Section: Introduction. In this section, we explore the advancements in enhancing the generalization of deep networks by regulating the sharpness of the loss landscape. One popular method, Sharpness-Aware Minimization, SAM, has shown remarkable performance in various image and language tasks, surpassing stochastic gradient descent, (SGD), by several percentage points. Notably, SAM excels in handling random label noise, outperforming SGD by a significant margin, especially in scenarios with 30% label noise in CIFAR10 dataset. SAM's effectiveness in combating label noise is most pronounced in a variant known as 1SAM, where perturbations are applied to each sample individually in a mini-batch. It is essential to note that in the presence of random label noise, the test accuracy does not necessarily improve with prolonged training but rather reaches a peak midway. Therefore, understanding SAM's behavior in this context requires a shift from focusing solely on its sharpness at convergence to considering its early learning phase. Even in cases with a single minimum, the optimal test accuracy can vary depending on the optimization path taken. SAM's performance remains robust even with fewer parameters, and in some instances, its advantages over SGD increase with more data. Our investigation delves into why 1SAM exhibits greater resilience to label noise compared to SGD at a more detailed level. By breaking down the gradient of each example into components related to the loss function and the network's Jacobian, we analyze how SAM's perturbations impact these elements separately. In linear models, SAM essentially prioritizes the gradient contributions of low loss points, particularly beneficial when dealing with mislabeled examples. This emphasis on clean examples during training helps prevent overfitting to noisy data, ultimately leading to higher test accuracy. In deep networks, SAM's approach of upweighting gradients for low-loss examples also proves effective. However, the impact of SAM's perturbations on the logit scale is minimal, while focusing solely on the network Jacobian term maintains SAM's robustness. This suggests that SAM's resilience to label noise in nonlinear scenarios primarily stems from its Jacobian term. Further analysis reveals that a Jacobian-only SAM approach for a two-layer linear network simplifies to SGD with L_2 regularization on the final layer weights and intermediate activations. This regularization mechanism helps maintain the performance of SGD, showcasing the potential benefits of constraining network output magnitude. While these insights shed light on SAM's label noise robustness, it is crucial to view these methods as complementary rather than standalone solutions. Our findings suggest that SAM's effectiveness against label noise may not solely arise from sharpness properties at convergence but also from the optimization path followed. Section Summary. In this section, we explore the effectiveness of Sharpness-Aware Minimization, SAM, in handling label noise compared to stochastic gradient descent, SGD. SAM, particularly the 1SAM variant, shows significant robustness to label noise by upweighting the gradient contribution of low loss points, which helps in achieving higher clean training before overfitting to noise. Additionally, SAM's perturbation on the network Jacobian term plays a crucial role in enhancing label noise robustness, suggesting that SAM's effectiveness lies in its optimization trajectory rather than sharpness properties at convergence. Section: Objective. In this section, we examine the logistic loss function for binary classification using the sigmoid function. We aim to find the gradient of the logistic loss function with respect to the model parameters. The logit scale, representing the model's confidence in predicting the incorrect class, influences the Jacobian term. This analysis extends to multi-class classification using cross-entropy loss with softmax function. We find that insights from binary classification apply to multi-class scenarios as well. Sharpness-Aware Minimization, SAM, focuses on finding a flat minimum of the training objective by minimizing a specific function that considers the magnitude of adversarial weight perturbations. SAM approximates the worst-case perturbation using the normalized gradient. However, a simple SAM update does not outperform SGD unless applied with a small batch size. To address this, we propose one SAM, which computes the adversarial perturbation for each example in the minibatch individually, leading to improved performance. In our study of one SAM, we explore variants like logit SAM, LSAM, and Jacobian SAM, JSAM, to understand their effects on model robustness. We find that JSAM performs similarly to one SAM in deep networks, while LSAM does not show the same level of improvement. For linear models, SAM enhances the gradients of low-loss examples, particularly through the logit scale term. Experimental results on linear models trained on Gaussian data with label noise demonstrate that SAM leads to higher early stopping test accuracy compared to SGD. By up-weighting the gradient signal from low loss points, SAM prioritizes fitting clean training data before overfitting to noise, resulting in improved test accuracy. Section Summary. In this section, we focus on the logistic loss function for binary classification and introduce Sharpness-Aware Minimization, SAM, to find a flat minimum by minimizing an objective that considers adversarial weight perturbations. We delve into one SAM, a variant of SAM that computes perturbations for each example individually, showing improved performance. Additionally, we explore hybrid 1SAM, isolating the effects of perturbations on the logit scale and Jacobian term, observing that Jacobian SAM performs similarly to 1SAM in deep networks. Section: Analysis of SAM's logit scale. In this section, we analyze SAM's logit scale. We recall that during a 1SAM update of a data point, x_i, t_i, the gradient is calculated at the weights perturbed by the normalized sample-wise gradient. In linear models, the perturbation is the example scaled by the label, given by epsilon_i equals rho t_i frac x_i, vert x_i vert. By evaluating the gradient at this perturbed weight, SAM's update simplifies to a constant adjustment of the logit scale by the norm of the data point. Since the sigmoid function sigma increases monotonically, adding this extra positive constant boosts the gradient norm of all training points. However, within points of the same norm vert x_i vert, this adjustment results in low loss points being upweighted more than high loss points, as proven in the lemma regarding preferential upweighting of low loss points. We interpret one SAM as a gradient reweighting scheme, where the weight, for example x_i, is determined by applying the lemma. By setting specific values, we demonstrate that low loss points are more influenced by the upweighting compared to high loss points. SAM favors upweighting the gradients of clean points since the loss decreases faster for clean points than noisy points. This preference leads to SAM achieving a higher early stopping test accuracy than gradient descent through induction. For our toy data distribution, we observe that the test accuracy plateaus as rho approaches infinity. Specifically, one SAM converges to the Bayes optimal solution. Additionally, in line with previous studies, we find that even in this linear scenario, one SAM behaves distinctly from the naive SAM update, with the latter not yielding any performance improvements from SGD. We delve into the asymptotic behavior of one SAM and the behavior of NSAM in the appendix. Moving on to neural networks, we explore SAM's robustness in relation to the Jacobian. From our linear analysis, we understand that SAM's logit scale term favors upweighting the gradients of low loss points. We confirm that this effect of SAM is also evident in neural networks. While this effect persists, we show that, contrary to expectations, the logit scale component of one SAM is not the primary reason for SAM's enhanced robustness in deep networks. Applying the one SAM perturbation solely to the Jacobian term, JSAM, largely recovers the gains of one SAM, while solely reweighting the logit scale, LSAM, does not. Moreover, a significant portion of the performance gains can be regained through a simpler regularization mimicking the effect of the one SAM Jacobian on just the last layer weights and activations. Explicit reweighting alone does not fully elucidate SAM's advantages. We observe that the upweighting of low loss points is noticeable even in multi-class classification with neural networks. The gradient for multi-class cross-entropy loss involves the softmax function and one hot encoding of the label. The corresponding logit scale component for multi-class classification scales with the loss. Our analysis in ResNet18 trained on CIFAR10 using SAM reveals that the norm change of this component after the SAM perturbation is higher for clean examples than noisy ones. While this observation suggests that explicit reweighting explains SAM's robustness in deeper models, applying SAM solely to the logit scale term shows marginal performance gains above SGD. Conversely, JSAM recovers most of SAM's gains, indicating that the logit scale reweighting is not the primary factor in SAM's robustness in neural networks. This observation holds true not only in deep networks but also in simpler linear networks and ReLU MLPs trained on CIFAR10 images with label noise. Previous studies attribute neural network robustness to logit scaling under label noise, but we argue that the direction or the network Jacobian of SAM's update plays a more crucial role. Section Summary. In this section, we analyze SAM's logit scale and its impact on gradient reweighting, showing that SAM preferentially upweights the gradients of low loss points, leading to improved robustness. While this effect is visible in neural networks, applying the SAM perturbation solely to the logit scale component does not explain SAM's gains, with the Jacobian term playing a more significant role in enhancing robustness across different network architectures and datasets. Section Analysis. In this section, we explore the impact of changing the Jacobian in a simple two-layer deep learning network. In the linear scenario, the Jacobian was fixed, but in the nonlinear case, it becomes sensitive to changes. Specifically, for two-layer deep learning networks, JSAM helps to regularize the size of the intermediate activations and the weights in the last layer. We prove this through a proposition that highlights the regularization effect on these components in a binary classification setting. To understand this better, let's consider the JSAM update for the first layer of the network, where the intermediate activation is denoted by Z and the normalization factor is represented by J in the second layer. The gradient with respect to the weights is also influenced by this normalization factor. Empirically, we observe a similar regularization effect in deeper networks when using JSAM. As networks become more complex, the JSAM update process becomes more intricate than just using standard SGD with regularization on weights and features. However, when we apply JSAM to train ResNet18 and monitor the sizes of the intermediate activations and last layer weights, we notice a significant decrease in their sizes. Building on our analysis, we conduct experiments by training deep networks using SGD with L_2 regularization on the last layer weights and intermediate activations of the last hidden layer. We simplify the regularization process to focus on the last layer weights and intermediate activations. Our experiments are carried out on CIFAR10 using ResNet18. We find that 1 SAM leads to unstable optimization when combined with batch normalization, requiring individual data point processing through the network. To address this, we replace batch normalization layers with layer normalization. By keeping other parameters constant, such as learning rate and batch size, we compare the performance of different optimization methods. Although regularized SGD does not match the test accuracy achieved by SAM, the performance gap decreases significantly. Furthermore, we explore the connection between logit scale and Jacobian terms. By regularizing the Jacobian, we aim to control the gradient contributions effectively. This regularization helps in maintaining a small network output magnitude, leading to better training outcomes. We also discuss the implicit bias of SAM and its impact on network training and generalization. Our analysis sheds light on the importance of, for example, regularization in SAM, especially in scenarios with random label noise. Section Summary. In this section, we explore the impact of perturbing the Jacobian in a simple two-layer deep linear network. We find that in nonlinear cases, the Jacobian becomes sensitive to perturbations, leading to regularization effects on the norm of intermediate activations and last layer weights through JSAM. Empirical results show that this regularization also benefits deeper networks like ResNet18, improving generalization under label noise. Section: Connection between sharpness and generalization. In this section, we explore the relationship between sharpness and generalization in deep learning. Sharpness of the loss landscape is often used as a way to measure generalization in deep learning. Various optimization techniques, such as adding noise to mini batches in stochastic gradient descent, using a large initial learning rate, and implementing dropout, have been found to guide the model towards solutions that lie in flat regions or areas of low curvature. However, it is important to note that the negative relationship between generalization and sharpness is not always true and depends on specific optimization choices. For instance, while strong data augmentation can enhance generalization, it may also sharpen the landscape. Additionally, there is a concept of sharpness regularization in adversarial weight robustness, although it is distinct from the label noise robustness that we focus on in our research. Dealing with mislabeled data is a common issue even in well-known datasets like CIFAR and ImageNet, and it can significantly impact the performance of a model. Our findings suggest that the key to improving generalization lies in how quickly the model learns from clean examples compared to noisy ones, building on previous studies that highlight the faster learning rate of clean examples in gradient-based optimization. This phenomenon has been demonstrated in linear models and more recently observed in neural networks, where the gradients for clean and noisy examples initially show negative cosine similarity during training. By examining the early learning behavior of clean examples based on their contribution to the average gradient, we can gain insights into the learning process. Many practical metrics also consider learning time to distinguish between examples that are effectively memorized by the model.